Okay, class. Today we're going to talk about how we make ether. So last lecture we talked about, we just kind of got introduced to what an ether is and the physical properties of ethers. And today we're going to talk about how we make ethers. So let's talk about, so again, because ethers are used as solvents, and one of the most common solvents that are used in chemistry is diethyl ether. And it's also a really common solvent used for extractions. So we need a lot of this. So because we need a lot of this, we want to be able to make this on an industrial scale. So industrially, the way something like diethyl ether is made is by an acid catalyzed dehydration of ethanol. And so what this is you take ethanol under acid catalyzed conditions. So you do a proton transfer, so the oxygen attacks the proton on H3O plus. You make the oxygen a good leaving group. Remember, when you put the positive formal charge on the oxygen, it makes this oxygen more electronegative, makes this carbon more electrophilic. So another molecule of ethanol where the oxygen will come in and attack, and this is an SN2 process. And so you've made this oxygen a good leaving group, ethanol attacks, you kick out water, and then what you do is you do another proton transfer here to get to diethyl ether. And if you have what we call a symmetrical ether, right, where the two alkyl groups attached to the oxygen are the same, simple symmetrical ethers can be prepared this way. Now, what if we want to prepare an unsymmetrical ether? Well, then what we have to do is we have to basically make sure we make one of the alkyl groups the nucleophile, and then the other alkyl group the electrophile. And so what we do is we do a process called the Williamson ether synthesis, where you start with an alcohol, you deprotonate with a strong base, such as sodium hydride. You can also deprotonate to make, or you can also make the alkoxide using sodium metal or potassium metal. So this could either be sodium hydride. This could also be here, right here, this could be sodium metal or potassium metal, all right? So this first step makes the alkoxide. And once you make the alkoxide, this is nucleophilic, and then you can do an SN2 reaction on an alkyl halide, which is shown down here. So the Williamson ether synthesis is a two-step process. You deprotonate, you do a proton transfer. H minus, which is basic, removes the proton on the alcohol to give you the alkoxide. The alkoxide will then, the O minus will attack the electrophilic carbon of an alkyl halide in an SN2 reaction, kicking on X minus, to give you your unsymmetrical ether. Now, because this second step is an SN2 reaction, this reaction only works really well if this alkyl halide is unhindered. So basically, we're looking, ideally, you want the alkyl halide to be a primary alkyl halide or a methyl alkyl halide. You technically can use secondary alkyl halides, but once you start getting into the secondary alkyl halides, you're going to start getting the E2 elimination process to compete. So a lot of times what you want when you make these, when you use the Williamson ether synthesis, you're using methyl halide or ethyl, methyl iodide or ethyl iodide, something like that. Now the reason this becomes important is, let's say you want to make methyl tert butyl ether, shown here. And if you think about it, there are kind of two ways you could do this. You could use tert butanol as the alcohol, so we're going to use this part as the alcohol, right? And then this part as the alkyl halide. So I'm going to deprotonate to make tert butyl alkoxide, and then I'm going to do the SN2 reaction on methyl halide. Or I could use this part as the alcohol in the form of methanol, and then use this part as the alkyl halide, right? So I would deprotonate to make the methoxide, and that would attack tert butyl iodide. Now, this does not work because this iodide is tertiary, so the SN2 reaction is not going to take place. So when you try to make ethers by the Williamson ether synthesis in like a retrosynthetic sense, when you go retrosynthetically, you want to use the less substituted alkyl group as the alkyl halide, and you want to use the more substituted alkyl group as the alcohol. Another way you can think about making ethers is by trapping this oxymerconium ion that you make during the oxymercuration demercuration sequence. So remember from chapter 8, you could take an alkene, you could do the oxymercuration to make the merconium ion, and then that merconium ion is opened up with water, right? So and again, this is what happens here is because this merconium. So if I'm going to draw, I can draw this really quick just to Make sure you remember this whole process. So the way this works is you have the double bond here. The double bond will react with the mercury acetate here to make the merconium ion. And because this next step, the water will open up this merconium ion here, right? And because this merconium ion, this mercury is positive, remember this bond is longer. So this is an SN2 opening, but this bond is actually longer, making this carbon more planar. So you actually attack this carbon and open up the merconium ion to give you the Markovnikov addition of water across the double bond. But there's no rearrangements in this reaction. So this is the advantage of using the oxymercuration demercuration sequence. You could make ethers in the same way if you replace the water with an alcohol. So if you replace the water in an oxymercuration demercuration sequence, you can then make ethers the same way. So so in this case, what's going to happen, the double bond is going to react with the mercury to make your merconium ion. And I'm going to draw the merconium ion bond here longer so you get a sense of what I was talking about with the merconium ion here. So here, because this carbon is more substituted, right, the partial charge is more easily to be formed on that carbon there, okay? So the carbon that's going to be attacked is this more substituted carbon in an SN2 reaction. I know this is counterintuitive to what we think about the SN2 reaction, but you got to keep in mind what's actually happening here, right? This bond is already breaking. This bond, so these three atoms, these three bonds become more planar. There's not very much steric hindrance there. So what happens then is your alcohol can open up your merconium ion. So this is what happened just like in the previous slide with water, but instead of water opening up, what you have is you have an alcohol opening up that merconium ion. And you can see now how we have, we've made an ether here. Once I deprotonate, right, I'm going to have made an ether here. So there's acetate floating around, so I'm going to remove that proton there to make my ether. So this is just another way to think about making ethers. So let me know if you have any questions. I hope that all made sense. Thanks for watching, and I will talk to you later.